and we're talking about the simple harmonic oscillator. And this is fundamental to quantum mechanics. So, dissection of a simple harmonic oscillator between two boundaries is key to understanding the different wave and energy states of an electron or any subatomic particle. But the electron is the particle of interest because it exists statistically in different waveforms as it rotates around the nucleus of the hydrogen atom or nucleus period. So understanding how that works on a quantum level is key to understanding the bulk of quantum mechanics. You can then start talking about discrete states, discrete energy states, momenta, all the different types of physical properties could be talked about in terms of integral multiples of a fundamental, meaning that you have a ground state and then you have jumps from that ground state. So the harmonic oscillator is key to the baseline understanding, and so much involved with that. But on our level, we're going to just take a look at waves in an easier sense by way of looking at the restoring force here. The spring force, Fs, is equal to negative k delta y, because we're in the vertical axis, is equal to mass times acceleration, because that's the only force of interest that's going to be the restoring force, that's going to be the force going back to zero, right? So the spring or restoring force, newtons. One thing I didn't say yesterday is that the spring constant k is newtons per meter, because you can see that instantly. If you divide force over delta y, it's newtons per meter. So that's the k constant. And then I went on to divide the mass, negative k delta y divided by mass, to get the acceleration expression. And that's going to be key to solving the differential equation that will give us the cosine function that we have up top. But I'm not going to do that here. Do that when we get to the calculus stuff. So then you can just see everything. It's very important to see where stuff comes from. All right, so the spring force is directed to the unstretched position. So like the professor yesterday had the spring just sitting at a 0 point. He stretches it, so the spring force is always going to try and go back to where it started. This up and down action. It's trying to restore balance. And so what happens over time is, friction is going to take over, and it's going to start bobbing less and less and less about the equilibrium, and then it just comes to a stop from where it was in the beginning. The spring force is conservative because it's the same magnitude above and below. That's why it's always going to go between the whatever extreme you pulled it down to. If you pull it down from 0, like say for instance right here, I can get my pointer. You pull it down right here. It's always going to go, say if that's -1, it's always going to go up to +1, with the spring force always trying to get back here to 0, back to balance. So that's the realistic picture. The ideal picture, of course, is going to bob and weave in the same two intervals, displacements forever and ever without friction. And that's completely the physical description or application of the sine and cosine functions, because we know mathematically that sine and cosine function cannot exceed the limits, the top and bottom magnitudes. And we know that, mathematically is undefined elsewhere, and physically that's what we see. And so that's why this action can be described by one of or both of those periodic functions. We start off with the cosine function, as we see here, negative cosine, and then the derivative of that will be a sine function, as we see in the second part, and then the derivative of that will be another cosine function, as we see down here. So those are the alternating states of this mass on spring, the position time function to the velocity time function and the acceleration time function, all simultaneous. And so we're going to see today that the acceleration is maximum at the extremes, because once it gets to the extreme +1 or -1, the restoring force is always going to be directed to the center at a maximum value. And since the force will be a maximum value, the acceleration will be a maximum. We know already from first principles that those directly depend on each other, right? So it all has this kind of beautiful harmony, harmonic oscillator. It's beautiful in its, its simplicity, and it's baseline fundamental to quantum mechanics to understand how this stuff works. And we can have a better appreciation that pretty much everything is born out of waves. There's something called matter waves, that everything that's material is made out of waves, as well as we have waves in a medium that we don't commonly associate with particles, sound waves, and that sort of business. But everything is waves. Everything is frequencies. And I'm coming to find out that Tesla was, he knew more than we can appreciate, right? When he made the statement himself that it's all about electromagnetism. And we're finding out slowly but surely that he was right. I mean, he's kind of undeniable. So as a side note, so there's that. So I want to draw simultaneous pictures of the displaced mass and then the graphs associated. So if I can just move this out of here. He would have, I yeah, don't get me started. Yeah, yeah. So anyway, we have this, let's try to get in here. And so we have this mass stretched to this amplitude. We call it negative A because it's below the zero here. And we'll call this, at this point, we'll, yeah, this would be t equals 0. So this is the first point in time, and the graph. So this is unstretched, and so the spring force is going to go right to this 0 point. So it's directed upward, because the spring force is always going to be opposite the direction of the mass. The mass goes down, spring force is up. Mass is up, spring force down. Alternating currents, alternating frequencies, alternating force directions. Everything's harmonious. All right, so we have our graph, and then let's say that this was positive A, and try and do this here. It's going up, going up. To make space for this negative A. And then our associated function is going to be y equals negative A cosine omega t. We're not worried about phase shift, so we just leave it out. Plus 5 is 0, the cosine function. And so if the angle, so this is going to be in radians. This is going to be amplitude versus angle, and then this is going to be pi over 2 pi 3 pi over 2 2 pi. And so for theta equals 0, this becomes negative A cosine of 0, because remember, omega t is theta from yesterday. And so angular displacement, or x equals vt, theta equals omega t, so that's theta. And okay, And theta is 0, cosine of 0 is 1, so it's minus a. So at time equals 0, our first point is there, right? And so then we go to t equals a quarter interval, because now it's a whole period and it's broken up into 4 parts. So this is a T4, T2, 3T4, and then T, right? So, and it comes back up to 0, the position 0. And which in radians, that's the pi over 2. So unit circle. So it starts off at 0 degrees, okay, which is our first position at t equals 0. Then it goes a quarter period to pi over 2, okay, which is this position, y equals 0. And then it goes half a period to pi, and 3/4 of a period to 3 pi over 2, and a full period at 2 pi. So it's unit circle all the way around. So at this point, there's no spring force at that instant because there's no displacement, because Fs is negative kx, k delta y, you know, kd displacement. So this is going to be no spring force. And then we have an associated graph. Debated whether I should have just drawn these out beforehand, but we can follow that for our edification. So a negative a. And so then we go, and now the function will be y equals negative a cosine pi over 2. Angle theta now, it's not 0, pi over 2, and then pi, then 3 pi over 2, and 2 pi. And so now it's space and time we talked about yesterday. Even though I don't label these in terms of time, this is going to be t over 4, t over 2, 3t over 4, and t full period. So the full period of time, t, is equivalent to the 2 pi period in radians. Same. So space and time, so this is going to be a curvature up, because starting a cosine function, negative cosine function. In this case, starts up below and comes up. So it's just the reflection of cosine. Yeah. So there's that. And move over here. And so then we have positive A, and the spring force will be directed down. And it's 0 right there in the middle. Trying to get my leverage here. Okay, so now, pi over 2, pi. It should be very familiar to all of you. I think you should be the trig part of your life, huh? Okay, so negative A. But if not, ask away. So now we've done here, we've gone here, and now the function says y equals negative a cosine of pi. Cosine of pi is -1 times negative a plus a. That's why it will come here. That, and then you can see it, you see the pattern. So here y equals negative a times -1 at pi. This is T equals T over 2. And T is 3/4 of a period. Come back down to y equals 0, if you will. And so there's no spring force at this point. And we're going to see that there's maximum speed at this point. We saw that yesterday. But a graph, hold on. Two pi, right? So then, so at that point, there's no spring force because the spring is at the same length it would be during rest, right? Yes, there's just no displacement from 0 because our relative, our reference point, I want to say, is 0. And so the displacement of the spring is going to be with respect to 0. So at this point, it's at 0, so nothing, no spring force. There is spring force here because it's got an amplitude or displacement, and likewise over here. That's all that's going on. So you put the mass, you just let it go. You haven't stretched it or anything. And then when you stretch it, the spring force is saying, nope, I want to get back to where it was at the very, very beginning. It's directed here. All right. So now at 3t over 4, our angle is 3 pi over 2. You know, cosine of 3 pi over 2, 270 is 0. So now we're going to do this, then this, and come back down like that. So their periodicity. So you can see the similarity between the mass on the spring to the wave function to the unit circle, all happening at once. And we're going to see that a full period of a wave is basically its wavelength. We can find its frequency. We know the period is just that. Then we can go crazy with it. Angular frequency, you know. So when it was heading upward, but the spring force was 0 at t over 4, what force was acting on it that brought it upwards? There's no force, because we're going to see that at that point that it's that there's maximum kinetic energy that's keeping it going. So there's no force at that moment, because what's happening is that the energy, that we can talk about it in terms of energy, that the energy at the amplitudes is potential, and that potential gets converted to kinetic maximally at 0. And that's why it flies through 0. But that's to come. So to your initial question, no force is at 0 for that moment. Its movement is a conversion of potential to kinetic, but that's you know, a question that we're going to address very soon. So now, after we get to 3t over 4, we go full period, and now it's back to where it started. At negative a. So remember, even with conservation of energy, we never considered forces. We're looking at the motion of this guy Forces are going to be considered for a particular reason, but you know, there's no net force at 0. All right, so this is minus A. We got that point here. And so we know cosine of 2 pi is just 1. And so this becomes negative A. So negative A. Full period. Up, over, down, and back. So that's a full period of time t. A wavelength is just a distance between the same 2 points, or the distance between the same starting and stopping point. So that would be a wavelength. Okay. And it has particular resonance with frequency. Speed is lambda times frequency. Speed of light, lambda times frequency, and then we can infer, we can get the different frequencies based on the wavelengths of the electromagnetic wave if we're considering electromagnetic waves. So higher frequencies have smaller wavelengths. A gamma ray, X-ray, they all occur in the same period. So this would be this wave. So a gamma ray, for example, would be something like this. It would have many cycles in the same period. It would be more frequent. Its wavelength is very short, but they both would be traveling at c. And that's another subject for another day, but in our context, c, constant. And yeah, wavelength is short, frequency is large. You have more cycles. So next thing, so yeah, there's that. So for our context, we know that and phi for the most part is going to be 0 because we can make this a sine function. And then the velocity is just going to be the derivative of this. Again, chain rule, those of you who are familiar with that see exactly what's going on. So we take out an omega, and well, actually the derivative of cosine is negative sine, for those in the know. And since there's a minus sign already out here, it's going to be basically negative omega. So we take not only do we take the derivative of a function cosine, which is negative sine, we take out an omega as well. And so this is going to be negative omega A sine omega t. So that makes it positive. So so d dt cosine t is negative sine. Okay, but again, you don't have to worry about that for those who are not in calculus. And just period, I'm just giving you what the expression is so that we can move on with the physics of it. So, all right, and then acceleration, take another derivative of sine, which is cosine, and take out another omega. And so we're going to get the derivative of sine is positive cosine. And so we're just going to get plus another omega. So omega times omega, omega squared, a cosine omega t. Those would be your expressions for velocity and acceleration. A rotational velocity and A being treated as constants in velocity derivation. No, because we're deriving with respect to omega. A is a constant. Yeah, because if omega was a constant, we wouldn't, be deriving with respect to it. So it's a chain rule type deal. Well, chain rule operation. So here's my y as a function of t. Here's my velocity and my acceleration. So that's going to be key when we go forward. So omega is this angular frequency. It's like it's angular velocity, but contextually we call it angular frequency because we're looking at it in terms of frequency. Why are we looking at it in terms of frequency? Because period 2 pi over omega. And then, as we saw that yesterday, so omega will be 2 pi over t. And since frequency is 1 over period, omega is 2 pi f. Radians per second. I think at this point it's trivial to make too much of a fuss over angular velocity versus angular frequency. It's, the context is angular frequency here. So that's another term, and we saw this, and frequency is cycles per time. How many cycles happen in a particular period? Gamma rays, more cycles. This would probably be a microwave or something, right? So there's that. And then we are going to draw up our associative velocity and acceleration curves. So we've already spoke about yesterday, like you're going to have a maximum velocity plus minus omega a if theta is equal to pi over 2 or 3 pi over 2, because cosine pi over 2 is zip. Actually, this is a sine function, right? So sine of pi over 2 is 1, and then sine of 3 pi over 2 is minus 1. But let's get on with that. So v of t omega a sine omega t. And so now we have those 5 angles. Theta is 0, then pi over 2, and so forth. This is just 0, so there's no speed when theta is equal to 0. Then theta is pi over 2. We have a maximum, so that's just going to be 1. So that's going to be plus omega a. So these points, you're getting these points so we can graph, right, with respect to theta. Omega sine pi, that's 0, right? And then, so forth. Sine 3 pi over 2, sine 3 pi over 2 is minus 1, so that's going to be negative omega a. Sine 2 pi is 0. So we got all of our points. So we got 0, maximum, 0, maximum below 0, and then back to 0. So this is a sine function, as you can see there. It's somewhat straight. Okay. Pi over 2, pi negative a, and then positive a, and 0. And so we have 0 first, and we go to, there I go again. It should be omega a. I want to put my position coordinates. So omega a and negative omega a. So 0 to maximum, back to 0, back to negative, and then back to 0. True sine function. So let's go back to the position. At this point, at pi over 2, the mass is at position 0, y equals 0. And at 3 pi over 2, the mass is also returning to 0, or going through 0 again. So your question is, what force is causing it? It's no force. It's all kinetic energy. Because at this point is maximum speed, 1/2 mv squared. It's the kinetic energy. It has maximum kinetic energy at that point, so it has maximum speed at that point. That's why the mass flies through 0. It doesn't stop. It doesn't go from, oh, I'm at maximum displacement, and then, oh, now I'm at 0 displacement, 0 force, I stop. No, it's moving. The potential energy at the edges convert to kinetic energy exactly in the middle. As indicated by this graph, we have maximum speed at 0. So it's going to go through, it's going to keep moving. That's why. And of course, this each second and theta. And then, so I hope that you can see that. If you still have any questions, let me know. The acceleration, we know it's going to be plus minus omega squared a. If theta is 0, pi, and 2 pi, because now it's a cosine function, and cosine is a maximum at those angles, whereas sine is maximum at pi over 2, 3 pi over 2. And then, so we go, so 0, omega squared a, cosine of 0 is omega squared a. So cosine of 0 is just 1. So it's going to start off at the extreme. So at the maximum, at the amplitudes, the acceleration will be maximized, either in positive or negative direction. So that's positive. That's cosine pi over 2, that's just 0. And this is going to be negative omega squared a. 0. And then back to omega squared a. Okay, so we got our 5 points. Oops. And then, right, so we start off. Once again, that should be omega squared a. Then negative omega squared a. So basically, get our turns like so. That's a positive cosine. So again, if we know that this is going to be y equals 0, there is no acceleration in the middle. It's all speed. Maximum velocity. and the accelerations are maximum at the edges. So this is omega squared a and negative omega squared a, but those are amplitudes. So for example, this is simultaneous with the, if I can see this graph right here. So I pulled it down, the acceleration is going to be going upward or positive. And that's what we see here. At the same time that it's pulled down, the acceleration goes the other way up, it's positive. And then it gets to 0, there's no acceleration. Why is that? Because there's no displacement. And Fs at 0, so is he. And no force. And then we go down. So now that the mass is in the air, so on the y versus t is going to be like this. So it's maximum here. So therefore, the acceleration is going to be going to negative. But so it's got positive amplitude, right? It's up in the air, and the acceleration is going to be directed downward. That's why it's negative at this point. Questions? You guys see this harmony? See the stuff? How that works is just back and forth, and just it's really quite lovely when you know just appreciate how synergy goes back and forth. But that's the basic wave stuff. All right, so now I want to do a little chart, and then we can do an example. First example, and then maybe I have time to do. You guys can do a problem. Okay. This is just keeping it real quick. Maybe I can go single screen for this. So I wanted to make a chart to relate all of the forces and the energies, the acceleration and velocity, how it looks like. And you can see a chart, a similar chart for yourself when we go to the energy section 15.3, which we'll talk about on Monday. So on page 427, you can see the connections between all the energies, all the quantities in simple harmonic motion. I just want to make my little chart here. So so Fs, let's say is negative Ka. A is delta X. Potential energy 1/2 Ka squared, X squared. Acceleration plus minus omega squared A. Velocity plus minus omega A. And then kinetic energy 1/2 mv squared or 1/2 m omega squared A squared. And that's going to be key when we look at the total energy of a simple harmonic oscillator in 15.3, the equation that we can get for the total energy in the system. And we're going to then see the beginnings of why the amplitude of a wave matters for energy, which matters for volume and sound, intensity. It's all about the amplitude modulation, frequency modulation, radios. So we're starting to get to see the foundation of that. So if I have plus A, 0, and negative A, I'm then going to label which of these quantities where the maxima and the minima, the maximum or 0 are. So at plus A, the spring force is a maximum because it's see in the equation. 0 and then max. The potential energy, max, 0 and max. So like the instant that the mass is at A and negative A, the potential energy is maximized, 1/2 Ka squared by so momentarily it has potential energy of the spring, and then it converts maximally to kinetic energy right in the middle. So if this is maximum force, the acceleration is also maximum at the edges, as we saw in the graph and all that good stuff. And then conversely, the velocity is going to be 0 at the edges, maximum at 0, and then 0. So it's back and forth. And then likewise, so this is why the mass flies through 0 back and forth until friction takes over and it comes to rest. Questions on that? Okay, you can go to your section, page 424, example 15.1. All right, so here they want you, you have this block connected to a light spring for which the force constant is 5 newtons per meter, is free to oscillate on a horizontal frictionless surface. Because most of our, I just did it from the vertical because that's, contextually that's an example that I usually do and the one we saw online. But it's kind of hard to put a spring on the surface. It's just, it's kind of hard. The block is displaced 5 centimeters from equilibrium and released from rest as an active figure. They want you to find the period and all the other stuff. So just going through. That's fantastic. What am I doing? Okay, and then the displacement from 0, 5 centimeters, and the picture would look something like this. It's horizontal. Kind of hard to do that in class because it just goes all the way back to the wall. So the thing we want to do first in part A is to find the period T, but we have to find something else first before we find the period. Why is that? Because T is 2 pi over omega. So far we don't have an omega here, so we have to figure out what omega is. So omega, yesterday I gave you the omega squared, which is K over M, so omega will be square root of K over M. You only know that or get that when in the solution of the differential equation for force. But again, take it for granted right now and we'll derive it later, use it later. So it's 5 newtons per meter. As you can see there, 5 radians per second. Then T is 2 pi over omega. And that's the period. That's how much time it takes to go through one cycle. As you know. then the max speed. So, and it really doesn't matter, it's the magnitude. I didn't even ask you just the magnitude. The maximum speed of the block. Whether you say plus or negative, it's, you know, not a big deal. So we have the angular frequency, the amplitude is 5 centimeters. .250 meters per second. That is omega squared A. So that's for maximum speed. Of course, if you want to find velocity as a function of time, you use the whole function, and then acceleration as a function of time, you use that whole function, which is the velocity would be the omega A sine negative omega A sine omega t, and this is omega squared A cosine omega t. But it's maximum, so 5 squared times your 1.25 meters per second squared. And so it's a maximum acceleration at the edges, maximum velocity right in the middle, right through zero. So it's an alternating energy perspective. So it's wonderful. You're going to get where one thing is maximum and the other thing is minimum. Boom, bam, bam, you know. Feeds off of each other, alternates. So then we need to express position as a function of time, velocity as a function of time. You just basically take the expressions and plugging in the numbers. They go through the business of explaining that the phase shift is zero. It's kind of trivial. It has some uses if the phase shift was non-zero. But A cosine omega t. We know what A is, the amplitude, how far it is from zero, 0.050, 5 centimeters. Cosine 5t. And that allows you to figure out, for whatever moment in time, where the position, where it's going to be. Yep. Then we have negative omega A. At business sine 5t. And then this is going to be negative 1.25. Because it's going to be this squared, 0.25 squared, 1.25, 25 and 25. Right? So that's squared. So that's that. So now let's do an example. You guys can work on an example here, using the same thing. Any questions here? You can see it there. And I encourage you, when you're looking at this, when you're reading at this, to do like the what if scenarios, like they, you know, kind of like more thought into the problem. But that's that. Let's go to question 2 of the problems. So I'm going to do it here. Page 441, number 2. You guys work on that for a few minutes. Some practice. So We have this piston oscillates with simple harmonic motion. Again, simple harmonic motion implies that we have a force directed to the center, because all periodic motion is not simple harmonic. Right? So only one type of simple harmonic. So that its position varies according to the expression given below, where x is in centimeters and t is in seconds. At t equals 0, find the position, its velocity, its acceleration, the period, and the amplitude of the motion. I want you to do 2 and 3. Okay. Yeah, 10, 15 minutes if you need that.